In this video, we will discuss the problem search in rotated sorted array. The problem has been asked previously in companies like Flipkart and Amazon. So let's have a look at the problem here. Problem says that we'll be given a sorted and rotated array which is having distinct elements, and the task is to find the index of the target element. If the target element is not present, then we have to return -1. For example, if you will see this array, so we have got 5, 6, 7, 8, 9, 10, then we have got 1, 2, 3. So the array is a sorted rotated array here, and the key value is given as 3. So is the element 3 present? Yes, it is present. So we'll return the index. Index is 8 here. Now if you see the next test case, so we have been given 3, 5, 1, 2. The key element that we are looking for is 6. Is 6 present? No. So return the element index as -1. That is, it is not present. So key is given as 42 and the array is 33, 42, 72 and 99. So this is a completely sorted array. So we can see here that we can find the index of the element 42 at 1. Okay, so it is present. So how can we solve this particular problem here? So we can basically apply one brute force approach, that is linear search, and we can try to go to every element of the array and we can try to search whether it is equal to the key element or not. At whichever index we are able to find the key element, we can return that particular index. In the worst case, what will happen? We have to iterate throughout the array. Okay, so we have to do maximum n iterations. So the time complexity for the linear search will be order of n, because in the worst case we'll be iterating throughout the array if the element is not present. Okay, and the space complexity will be order of 1. But can we solve this problem more optimally? Yes, because the array has been rotated and it is a sorted array, right? The sorted array was rotated, so we can apply binary search here. Okay, now there are two ways in which you can apply binary search. So we'll discuss the first way, that is a better approach than this one, and then we'll discuss about the most optimal approach of binary search also. So let's discuss this. Suppose that we have been given an array which is sorted rotated. Now what we can do is we can try to find the pivot index in that array. Now what do we mean by pivot index here? The pivot index will be the index of the minimum element in that array. Okay, now why will we find this? You will understand very easily. Suppose that if the array was like 0, 1, then we had 3, then we had 5, 7, 9. Suppose this was the array here, and for finding the pivot index also we will apply binary search. We'll discuss the code for it as well. We'll discuss the logic for finding the pivot as well. But firstly, let's discuss that suppose we have the pivot index, how it is going to help us to solve this problem. So if we know the index of the minimum element here, suppose the index of the minimum element is the starting index itself, that is the array 0, 1, 0, 1, 3, 5, 7, 9. In this, the pivot index will be at the starting only. If the pivot index or the index of the minimum element is 0 only, right, is the starting index only, then the whole array is sorted. And for searching the key element, I can apply simple binary search. Whatever key I have to search, if the whole array is sorted, when can I say that the whole array will be sorted? If the index of the minimum element is the actual starting index of the array itself, then that array is completely sorted. If the minimum element lies at the very first index, this means that the array is completely sorted, and if it is completely sorted, apply a normal binary search here for searching the key. But if the pivot element is present in between, then what should I do? Pivot index or the index of the minimum element, if it is present in between, then I'll check that whether the element at the pivot index or the index of the minimum element, whether this element is equal to the key or not. So is this element equal to the key here? No, this particular element is not equal to the key. So if it is not equal to the key, so what can I observe? You can observe here two things. One is that this left part, the array on the left side of the pivot, it is completely sorted. And array on the right side of the pivot, including the pivot, is also sorted. So there are two arrays which look like sorted here. Okay, so what can I say? I can simply say that suppose if I have to check, like I have checked that whether the minimum element is equal to the key or not. So is 0 equal to key? No. So now where should I search? That will be dependent on the value present at the starting of the array. So if you check the element at the 0th index, that is 4. So what is there at the 0th index? The element is 4. Is it greater than the key? As of now, it looks like it is greater than the key, because 4 is greater than 2 here. If the element at the 0th index, if it is greater than the key, this means that on the right side of this element 4, on the right side of this 0th element, all the elements are also greater, because you can see that the elements are increasing, and then I have the pivot where I find the minimum element. So if the element at the 0th index, if it is greater, you can observe this carefully, that element at the 0th index, if it is greater than the key itself, then all the elements on the right, if the element at the 0th index, if it is greater than the key, all the elements on the right side are also greater than the key. So the searching should not be done at this part. Where should I search? I should search from the pivot till the end of the array. Because if the element at the 0th index, if it is greater than 2, all the elements on the right side of the 0th element will also be greater until I reach pivot. So the key will lie including pivot till the end of the array. Because you can see, I need to search where? I need to search if the element at the 0th index is greater, all the other elements are greater. So search from the pivot till the end of the array. So you need to apply binary search starting from the pivot till the end of the array. So we will do what? We will call the binary search function, and we'll basically start it from the pivot index till the end of the array. Okay. Otherwise, what can happen is, another thing that can happen here is, suppose that my key value is equal to 6 here. Okay, if the key value is 6, now what will happen in this particular case? If you'll observe here, so the element at the 0th index is 4. Now 4 is what? 4 is basically less than equal to 6 here. Okay, so this means that if the 0th index element is lesser than the key, in this case we need to search on the left side of pivot, because you can see 6 is lying on this particular side. So we need to search from where to where? We need to search in the L, like in this case, when the 0th index element, if it is, let's say, less than equal to the key, then we need to apply the binary search from the 0th index till pivot minus 1. Okay. Because if you see, if I had to search for for an element which was 6, or any element which where ARR of 0 is less than equal to key, if I have to search for any key where this condition is getting satisfied, then I have to search from 0 till pivot minus 1. You can see here, if I keep 4 here, 5 here, or 6 here, 7 here, any element, so I have to search from 0 till pivot minus 1. So that is where I'll apply my binary search. So this is the logic here. So you can see here, what we will be doing is, let's have a look at the basic implementation, then we'll discuss the finding of pivot element, or the pivot index, which is the index of the minimum element as well. Okay, so when I say pivot, I'm referring to the minimum element here. Okay, index of the minimum element here. Now if you see, we will first of all find the length of the array. We'll find the index of the minimum element here using this function. Once we have done that, then we'll check if the key element is the minimum element itself, then we'll return the index of the minimum element. Otherwise, we will check that if the pivot index is the 0th index itself. So if the minimum element is present at the 0th index, this means that the whole array is sorted, and for searching the key we can simply apply a binary search from 0 till the end of the array. Otherwise, if that is not so, then we'll check what did we check? We check that if the 0th element is less than equal to the key, then we need to search from 0 till pivot minus 1. Correct? Because if the key was either equal to 4, 5, 6, or 7, then we were searching starting from the 0th index of the array till pivot minus 1, because that part is greater now. That is why. So we'll search in this part. So you can see here that if the ARR of 0, if it is less than equal to key, then you will search from 0 till pivot minus 1. Okay. Otherwise you can search where? Otherwise you can search from pivot plus 1 till the end. So as I said, suppose that if my key was equal to what? If my key was equal to, let's say, 2 here. Okay, so if 4 is greater than 2, then what will happen? I need to search from where? I need to search from pivot plus 1 till the end of the array. So I need to search from, because if 4 is greater than 2, all the other elements on the right of 4 are also greater until the pivot. So I need to search from pivot plus 1 till the end of the array for this particular key here. And that is what we have done in this particular code here. Now the interesting thing is that how do we find the pivot also using the binary search? Because you can see that if I know the index of the minimum element, that is my pivot, okay, then the task becomes easier. But how do we find the minimum element index using the binary search? So you can see here, what we will try to do is, we'll try to run the binary search if we have at least more than one element. Because if we have got only one element, then we can stop doing our binary search. So we will apply binary search until we have a single element remaining. If the low is less than the high, this means that we have two or more elements. If we have two or more elements, we'll keep on searching. But once we have a single element, then we will stop. Okay. Now there can be a situation, suppose something like this. Suppose if I had an array like 0, 1, 2, 3, up till 8 here. Okay. Now suppose if my low is lying here and my high is lying here. If my element at the low index, if it is less than equal to the element at the high index, this means that the element at the low index, it is the minimum element. So I should return that particular index here. Correct. This is one situation. But another situation can be like this also. Suppose that if I had an array which was like this 7, 8, then I had 0, 1, 2 up till 5 here. Suppose. Okay. And assume that after certain steps, my low is standing here and my high is standing here. My high is standing at this point. Okay. Now, what will happen in such a case? You can see here that again, if my low is less than equal to element at the low index, if it is less than equal to the high, then the element at the low index is going to be my minimum element index. Okay, so I can return this low here. This is what I'm doing here. Correct. Otherwise, we can try to find out the midpoint. So suppose that if this scenario is not achieved, then we'll find the midpoint. So you can see here that my low will be standing where my low is standing here, suppose initially, and my high is standing here. Now, if I find out the midpoint, my mid will be this particular element. Now observe this. If the element at the mid index, understand one thing, if the element at the mid index, if it is greater than the element at the high index, this means what? This means that the element at the high index, if it is lesser, okay, so the minimum element will lie on the right side of mid, because if the element at the mid is higher than the element at the end of the array, okay, so this means that the element at the mid is higher and on the right side I'm having lesser element, that is why my high is less. So we need to search on the right side of mid for the minimum element. So we will do what? We will say that our low should be equal to mid plus 1 here, because the lower element or the smallest element will lie on the right side of mid for this kind of situation whenever the element at the mid index, if it is greater than the ARR of higher. Okay. Now another circumstance can be, suppose that if the array is somewhat like this, let's say if the range that I'm searching is, let's say 7, then I've got 8 here, then I've got 0, 1, 2, 3, 4. Okay, suppose this is the range that I'm searching for, and assume for a second that if this is my low, suppose this is my high, let's assume that my mid is standing here. Okay, so in this case, if the mid is not greater than the high, then where can the lower element lie? It can like where can the smallest element lie? It can lie in the range from low till mid, so it will lie in this range. Okay, so that is why we'll update that the highest index that we should search for is the mid index. Okay, because this is what will be the scenario here. So if the element at the mid index, if it is greater than the element at the high index, so this means that the minimum element or the smallest element is lying on the right side of mid, so search on the right side. Otherwise, if that is not so, so this means that the this means that the smallest element can lie between the low till mid. Okay, so it will lie in this range, so you can look for this. Okay, I've given just a sample example so that you can understand. I hope you have understood how we are finding the pivot here, as well as after finding the pivot, how we are applying binary search cleverly. Now let us discuss about the most optimal approach where we'll be solving this problem using a single binary search. So how can we use a single binary search for solving this problem? Before the before this, the approach that we have applied, it was using two binary searches, because one binary search we were applying for finding out the index of the smallest element, and then using that we were applying the binary search cleverly. But how can we do this using single binary search? So suppose that we have been given an array. First of all, let's discuss this array, that is 4, 5, 6, 7, 0, 1, and 2. If this is the array that I have been given, so assume that initially my low was at 0. So my low is here. High is standing at the end point. Then my mid will be what? My mid will be the element at the index 3. Okay. So in this particular case, what can I say? I can basically observe one thing very clearly, that the element at the low index, okay, if you see here, the element at the low index, is it less than equal to the element at the at the mid index? Yes. So what can I say? If the element at the low index, that is basically 4 here, if it is less than equal to the element at the mid index, that is 7, so this means that the left half of the array is sorted. Okay, as of now you can understand that the left half is sorted. Okay, if I find out the midpoint and low is element at the low index is lesser than equal to the element at the high index, so my left half is sorted. How can I use it for my advantage? Now if I know that my left half is sorted, how can I use it? So basically, if my left half is sorted and suppose that my key is equal to 1 here, I know that my left half is sorted and my key is equal to 1. The element that I'm looking for is 1. If my left half my left half is sorted and the element that I'm looking for is 1. Now, should I search it in this left half? No, I should not. Why? Because if you will observe, the element, if this is sorted, uh, if the left half is sorted and the element at the low index, okay, if it is greater than the key, okay, if the element at the low index, if it is greater than the key, then this means that all the elements in this range will also be greater than this key because this is sorted in the increasing order. Correct. So I should search where? I should search on the right side of mid. Okay, so let's write this condition here, like what I'm trying to derive here. Okay, so what happens is if you find out the midpoint and the element at the low index or at the start index, basically, if it is less than equal to the element at the mid index, if this is the situation that we have here, correct. So in this case, we will try to check. We'll try to check what? That if the element at the low index, suppose if it is what? If it is greater than the key. Okay, if it is greater than the key, then what will happen? If it is greater than the key, so like if my key was equal to what? Let's say it was equal to 1 here, and the element at the low index is what? 4. So if 4 is greater, if my left is sorted, see my left half is sorted. If my left half is sorted and the element and the very first element of the left half is greater than the key. So this means all the elements in the left half will be greater than the key, and I should search on which side? I should search on the right side of mid. So I'll say that my lowest point should now become equal to mid plus 1, because actually I should search from mid plus 1 index till the end of the array. I should search from here, that is from index 4 till the end of the array. Okay, if my situation is like this. But suppose if the key element lies in the range, okay, suppose that another circumstance can be that if the key element lies in the range. So let's say my key element is equal to what? 6. Okay, so if I know that my mid is the element 7 here, okay, and my low is standing at 4, high is standing at 2 here, okay, and I know that low is less than equal to the mid, okay, so I know that the left half is sorted, and I also know that the mid is lying, and the mid is where the key is lying, okay, because suppose my key is 6. So if the key element lies in the range of low till mid, then I need to apply the my search in this range. So my low will remain the same, but my highest point of search will be this particular mid guy, okay. But if it is not equal, then I'll search inside. So I'll be searching from low till mid minus 1. So highest point can be mid minus 1. So in the else case, you can say that if my left half is sorted and the element lies in the left half, then the highest point of search will be mid minus 1 here, because if I'm searching for 6 here, so you can observe that if I'm searching for 6 and the element lies between 4 to 7 here, because 6 lies between 4 to 7, so it lies in the first half. So for this I have to adjust my high, and I have to make my high as mid minus 1. Okay, this is what I'll do. Now another situation will be when my left half is not sorted, because if you see, like what can happen is, if I have been given this particular array, so let's have a look at this array also. Okay, let's say we have got this particular array here. Now if you see, this will be my low, and if you will see, assuming that my mid will be somewhere here and my high will be here. Now in this particular case, what can I say? Is my left half sorted? No, it is not sorted, so I cannot directly say anything about the left half. But in this case, my right half is sorted. You can see that my right half looks like it is sorted here. Correct. Now let me just put the mid at the correct position. So you have got 0 1 2 3 4 5 6 7. So if it is 7, then it will be at the index 3. So 0 1 2 3. So yeah, mid will be standing here. Now if you see, so what can I observe here? In the else case, the right half will be sorted, because as of now I'll check, is the element at the low index, is it less than equal to the element at the mid index? No. If this is not true, then the left half is not sorted. So this means that the right half must be sorted, because the array is rotated only one time. So if the right half is sorted, then what can I say? If the right half is sorted, in the else case, when the right half is sorted, right half is sorted. So if the right half is sorted and the element lies in the right half, what does this mean? So if suppose that the key element that I'm looking for, okay, if it is basically greater or equal to the ARR of mid, okay, if it is greater than ARR of mid and it is what? It is less than uh, equal to, basically if if it is lying in this range here. So if it is lying in this range, then where should I search? I should search on the right side of mid. So my lowest point of search should be mid plus 1 here, because if the element was lying at the mid, then I would have already checked it. But if it is not lying at the mid and the element is lying in this range, okay, in the right, if the right half is sorted and element is lying in this range, then in that case my lowest point of search will be mid plus 1 here. Okay. Otherwise, if it is not lying in this range, suppose that the key element that I'm looking for is what? If the key element that I'm looking for, let's say, is equal to 8 here. Now, does 8 lie in this range? No, it does not. So I should search on which side? I should search on the left side of mid. So my highest point of search will be mid minus 1 here. So I hope you have understood this idea here. Let's discuss it in terms of implementation. So if you will see here, my low will be less than equal to the high. I'll find out the midpoint. After finding out the midpoint, if the mid index is is having the key, directly return that mid index. Otherwise, you check whether the left half is sorted or right half. So if the left half is sorted, basically if the element at the low index, if it is less than equal to the element at the mid index, okay, then in that case, the left half is sorted. So if the element is lying in the left half, if the key element is lying in the left half, then we need to search from low till mid minus 1. So my highest point will be mid minus 1. That is what I have already told in terms of code also. Otherwise, my low will be equal to what? Mid plus 1. This is what I had told when I was telling this example. That if this is this array that I have, and my low is standing here, mid is standing here, and high is standing here, and the key that I am looking for, assume that if my key was 6 here, so if my left half is sorted and the key is lying in this left half, then my highest point of search will be equal to what? Then my highest point of search will be equal to this mid minus 1, because I'll search from low till mid minus 1 here. Okay. Otherwise, if the element, if the left half is sorted and the element is not lying in the left half, then we'll try to search on the right side of mid. So we'll try to search from mid plus 1 till the end. So that is why my low will get updated to mid plus 1 here. So if it does not lie in the range, in the left half, which is sorted, then we'll try to search on the right side of mid. That is, low will be equal to mid plus 1. And in the else case, if the right half is sorted, so we have discussed this case when the right half is sorted. So if the element lies in this particular right half, okay, if the element is in between the elements of the right half, then we'll search from mid plus 1 here. So the low will be equal to mid plus 1 if the element lies in the right half. Okay. Otherwise, we'll search in the left half. So if assume that my key was 8 and element does not lie in this sorted right half, then we will look for it from low till mid minus 1. So the highest point will be equal to mid minus 1 here. So this is what we have to do here. We have to basically check whether the left half is sorted or the right half is sorted, and based on that we'll make the decision that we have to update the low or the high depending on the conditions here. Okay. Now time complexity taken for this code will be order of log n only, because we are just using a simple binary search. Space complexity will be order of 1 as well. If you see, we have done another approach, that is applying two binary searches. That will also take overall order of log n plus log n time. But if the interviewer will ask you to apply only single binary search, then you'll be using this particular approach. But in interview, you should first of all tell about the group, then the better approach using two binary searches, applying the pivot index concept, that is finding the minimum element, and then apply single binary search and do this. So let's now try and submit this problem also using the optimal approach. So we have written the code. Let's try and submit it now. So you can see here that my code is also getting accepted. I hope you have understood this problem clearly. And as I said, it has been asked in a lot of companies. And I hope that you're clear with the concept. Make sure to comment understood. Thank you for watching this video.